Hello everyone, this is Rahul from Learning Simplified. In this video we are going to look at how a computer stores a real number. So let's get started. So far we have seen how a computer represents integer values, both signed and unsigned integer values, but here we haven't seen how it stores real values such as 3.14 or 2.71 or something like that. Now I want you to pause the video and think you are designing a computer, how you want to store these real values in your computer. So pause the video and think of it. I hope you have paused the video and thought of what idea you could apply. So there was a standard, IEEE standard of representing a floating point, where every computer uses this floating point representation to represent these real numbers. But before that, let us see what is a normalized form is. Normalized form. Generally, a real number can be represented as, suppose we have a number 113.927 into 10 power minus 6. Then in normalized form, we must have only a 1 before this decimal point, such as 1.13927 into 10 power minus 4. This is the normalized form, whereas this is not a normalized form, or even 0.01 into 10 power 5, something like that is also not a normalized form. So let's get to the IEEE floating point number. The IEEE floating point number is, this is the IEEE floating point number, where the first bit is the sign bit, this bit is the sign bit, this is the sign and magnitude representation of a real number. This is a sign bit. If it is 1, then it is considered as a positive value. If it is 0, then it is considered as a negative value. This is an exponent value, and this is a fraction. It is also called as mantissa or fraction. The total size of this word is 32 bits. We have allocated 23 bits for the fraction, 8 bits for the exponent, and 1 sign bit. So 1.0 into 10 power 3, into 2 power 3. The sign bit for this value is 0, and the fraction is this 0, and the exponent is 3 converted into 2's complement form. This the generalized form is minus 1 power s into 1 point fraction. Fraction is nothing but this value over here, this fraction value, into 2 power e. E is nothing but exponent. The exponent what we store here is nothing but e. This is the general representation of floating point number, but this is not the standard that we are talking about. There is a slight change in the exponent that we store here. We modify the exponent, and why there is a need to modify exponent is, suppose we are sorting two numbers, we are sorting two integer values, then suppose we are sorting 1 1 1 0. In sorting we often compare two numbers, 0 1 1 1. While comparing, what hardware does is, it starts from the MSB position, it checks this bit of this number and the same bit of this number. These bits are different, this is higher value and this is lower value, so this number is greater than this number. What if we have 0 1 1 0 and 0 0 1 1? It starts comparing from this bit, both bits are same, so it goes to the next bit again for both. This has 1 here in here and this has a 0, so this number is again greater than this number. So how does the computer compare two floating point numbers? There must be some fast way to compare floating point numbers. If we can see this sign bit, that if the sign bit is 1, then it is a negative number. If a sign bit is 0, then it is a positive number. That is an advantage. But what if both numbers are positive or both numbers are negative? Then how do we compare? Let us take an example and try to see what I am talking about. Now let us write 1.0 into 2 power plus 1 in binary floating point value as, let's take this and what is the sign bit here? The sign bit is, it is positive number, so the sign bit is 0. What is the fraction value? Fraction value is 0. This one is assumed. We need not write this one here in the fraction values. This one is assumed, so the fraction is all zeros. Oh, it is not visible. Let's take this color. 0 0 0 0 0, all these bits are zeros. And how do we write a plus 1? We write a plus 1 as, the LSB is 1, and remaining are zeros. This is the representation of 1 into 2 power plus 1. Now let us write 1.0 into 2 power minus 1. 1.0 into 2 power minus 1. The sign bit is 0 here as well, because this number is positive, and the fraction is 0. All are zeros, but this is minus 1. Minus 1 we have to write in 2's complement form here. What is plus 1? 1, and minus 1 is, take the 2's complement of plus 1, which is 1, and start flipping all the zeros to ones. 1 1 1 1 1 1 1. Now what a comparison operator does is, to the comparison operator, this number appears to be a small number, but this number appears to be a large number because of all ones here and all zeros in the MSB starting positions. So what to ease the comparison, we manipulate these bits so that the negative values become smaller and positive values appear to be larger. So this is called as biased notation. That is, we add a number to this exponent number to make it appear as a big number, and we add the same number here to the negative number to appear it as a smaller number, and that bias number is in IEEE 754. That bias number is 127. that is, for plus 1 we add 127, it becomes 128. For minus 1 as well we add 127, which becomes 126. 128 we can write 128 as, now first write the weights, 1, 2, 4, 8, 16, 32, 64, 128. We can write 128 as 1, 0, 0, 0, 0, 0, 0, 0. 126 as, this is 0, 1, 1, 1, 1, 1, 1, and this is a 0. If you put a 1 here, it becomes 127, but 127 minus 1 is 126. Now let us check. This number is bigger than this number, which makes the comparison easy. So this is the essence of biasing the number in IEEE 754 floating point number. Many of us get confused why this bias is used. So this is the reason why we use the bias. Now let us generalize. We can write it as minus 1 power sign into 1 point fraction value into 2 power what we write here is, what are we doing here? We are adding 127 to the exponent value, right? Actually 1.0 into 2 power minus 1, for this value we are adding 127 to write 0, 1, 1, 1, 1, 1, 1, 0 here. But in order to get minus 1 back, we have to subtract 127 from this number. So exponent, don't get confused with exponent with this value. Exponent means this value in the IEEE 754 notation. The exponent value in here is this exponent minus 127. This is the notation. Generally, where we do mistake is calculating this part. We get confused too often. So let us practice more and more on this now. Let us suppose we have 1.1 1 into 2 power 12. Then what is the exponent value? This is the 12 value. What we should write in the exponent field? What value we should write in the exponent field? Let us calculate. We know that exponent minus 127 equals 12, because exponent minus 127 equals 12. Exponent is 127 plus 12. What is this? 7, 9, 3, 1. So the exponent value is 139. What is 139? Let's write the weights and check what 139 is. 1, 2, 4, 8, 16, 32, 64, 128, 256. 139 is smaller than 256, so let us put a 0 here. 128, what is the remaining here? 128, we have got 128, 1, 1. We are in need of 11 more. So put a 0 here, 0, 0, we put a 1. What is 11 minus 8? It is 3. So we are in need of 3. Put a 0 here, this. So this is the 1, 2, 3, 4, 5, 6, 7, 8. this is the value that we have to copy into this exponent field. Okay, now let us see one more example. 2.3 into 2 power 30. So the exponent value is exponent minus 127 equals 30. Exponent equals 127 plus 30, which is 157. Convert this value into binary and store this in the exponent. Now let us consider the whole thing, how to convert a big real number into form of bit patterns to represent it in complete picture. That is, let us have 0.75 base 10. Let's put a minus 0.75 base 10, and we have to represent this in 32-bit floating point number. 32-bit floating point number. What to do is, first let us consider this into binary. Convert this into binary. How do we convert a fraction? We multiply by 2. 75 times 2 equals 1.5. It is 1. We consider only 1. Next 5 is carried forward to next step. 0.5 times 2 is 1.0. We consider only 1. 0 is carried. 0 times 2 is 0. We stop it here. Now minus 0.75 base 10 is minus 0.75 base 10 is minus 0.11 base 2. Now we have to convert this into normalized form. What is normalized form? That the binary point, before the binary point there must be a non-zero and there must be no leading zeros. So normalized form is minus 1.1 into 2 power minus 1. We have seen this property in the last video. I have said this. If you haven't seen the last video, I recommend you to watch that video and come back here to know how I have written this value. So this is in normalized notation. Now let's convert this minus 1. Let's convert this into this form. 1 point fraction into 2 power exponent minus 127. This is equivalent to this. So let us derive all the values from that. What is the sign bit? Sign bit is 1 because it is a negative number. And what is the fraction value? Fraction is the value after the binary point, that is 1. We can append as many zeros as the 23-bit fraction value requires. And what is the exponent value? This value equals this value. So exponent minus 127 equals minus 1. Exponent equals minus 1 plus 127, which is nothing but 126. Now let us represent this in IEEE floating point numbers. So the sign bit is 1. We write a 1 here. Now the fraction is 1 0 0 0. We write a 1 0 0 0 and all are zeros. And what is exponent value? We write it here, 1 2, 4, 8, 16, 32, 64, 128. This is 0, this is 1, 1, 1, 1, 1, 1, 0. This is the exponent value. We write it here 0, 1, 1, 1, 1, 1, 1, 0. So this is the desired value that can be stored in the computer memory for minus 0.75 base 10. This is the equivalent IEEE floating point number representation. If you don't understand this right now, or you are getting confused anywhere or of how I am doing so fast, don't worry. In the next video we will practice as many examples as possible. So don't worry. Next we will see how we can convert a binary representation into a decimal value. So let's have a number, a floating point number. Some random number 1, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, and all are zeros here. Now let us convert this number into decimal of base 10. So write the general form first, into 1 point fraction into 2 power exponent minus 127. So what is the value of s? S is 0. It means this is a positive number. And what is the value of fraction? Fraction value is 0.01. The trailing zeros doesn't matter, they are of no use, so we write 0.01. Now gets the tricky part. What is the exponent value? Right, what we should write at 2 power here? We have already this value, so we substitute this exponent value here to get the power of 2. That's all. Which means let us rewrite this as, minus 1 power s into 1 point fraction into 2 power e. Let us say 2 power e. What is the value of e? The value of e is nothing but exponent minus 127. That's it. E equals exponent minus 127. What is the value of exponent? This is, let's write the weights first. This is 1, this is 2, 4, 8, 16, 32, 64, and this is 128. So the total is 128 plus 1 equals 129. This is the value of this exponent. So the value of E is equals 129 minus 127. E is 2. The value of E is 2. So the value of E equals exponent minus 127 equals 2. So the final number is minus 1 power s value is 0 into 1 point. This 1 is always assumed. We don't need to have 1 value here. This is implicitly assumed. By default this is 1 and the fraction value is 0, 1 into 2 power. What do we write here? We don't write this exponent value. we write the calculated exponent, we remove the bias. First we calculate the exponent value, we remove the bias because we have initially added 127 while storing into the floating point representation number. So this is 2. The number is this gets out 1.01 into 2 power 2. In the last video I have said this: if you multiply a real number by 2 in 2 binary representation, this decimal point moves to the right and this bit moves to the left, but we have two numbers, so the value is 101, which is equal to 5.0. This is the value in base 10 that we have stored here. So that's all for this video, guys. I hope you have enjoyed this video. See you next time. Until then, happy learning.